Hi, my name's Al Steinman. I am the Alan and Helen Hunting Research Professor at the Annis Water Resources Institute of Grand Valley State University. And I am going to be talking today about climate change. And so let me bring up the presentation. And I'm going to need to go back one. So what I want to do is start off talking a little about climate change background. And then I'll talk to some of the uncertainties associated with climate change, what the impacts are for our region, and then finally talk about what we can do to make a difference in terms of mitigating climate change. So first of all, we have a number of different greenhouse gases in our atmosphere that are contributing to the warming of our planet. Carbon dioxide gets the most attention because it's the most abundant of these compounds in the atmosphere. But in fact, other compounds such as methane and nitrous oxide actually are far more potent. In other words, they hold much more heat per unit molecule than carbon dioxide. In fact, methane is 30 times more potent than CO2, and methane's been getting a lot of attention lately. Let's see, and why am I not advancing? So if we look at the amount of methane that's been entering into our atmosphere over the last 40 years or so, you can see that it's been rising at a fairly significant rate, and that's causing greater concern. One of the sources of methane, of course, are cows and different types of ruminants coming out from both ends of the cows. In fact, as we'll talk about later, if we're talking about individual actions that we can take to make a difference, then not eating meat does make a big difference on a lot of different levels, and I'll get into that in a little more detail. With the Arctic area warming perhaps faster than anywhere else on this planet, what we're seeing is these frozen soils are starting to thaw, and as a consequence, their thawing is resulting in the emanation of a lot of these either carbon dioxide or particularly methane. And if we look at this map, you can see the richer the red colors, the faster they are the fastest thawing areas of the Arctic Circle. And that's also where most of this methane is coming from, out of these areas as the tundra starts to melt. If we look at CO2 emissions over on a planetary basis, we can see that they are continuing to increase. This is up to 2018. It had a slight dip during the COVID pandemic, and now it's back up again. And we can see that the developing countries, rapidly developing countries like India and China, are particularly increasing over time, whereas Europe and the United States has actually plateaued in their CO2 emissions. And then I've got this animation from NOAA that shows the amount of CO2 that's been entering the atmosphere from 2002 through 2017. And so let me start this, and you'll see the colors will start to warm. Here's the legend here on the lower right, looking at the CO2 concentration in the atmosphere. So the warmer the reds, the more the carbon dioxide. And you'll see that the CO2 accumulates largely starting off on the polar regions. And those are the areas, both the North and South Pole, where we're seeing the largest amount of CO2 accumulation and the highest rate of warming on the planet. And so now we're up into 2010, and you're seeing it particularly up in the North Pole, some in the South Pole as well. And then as we move forward into 2012, we're starting to see warming across the entire planet, but again, with those seasonal impacts, particularly in the northern latitudes and some into the southern latitudes. And by the time that we hit 2017, 2018, when this animation stops, we can see that the warming is going across the entire planet, and we're seeing some significant impacts associated with CO2. If we look at the temperatures on a planetary basis, what we're looking at here is the anomaly on the y-axis. That means the change from the baseline, change from zero. And back in the late 1800s, early 1900s, we were actually cooling across the planet. But then starting around 1960, we started to see this fairly rapid rise. There was one blip back in 1991, 92, when Mount Pinatubo in Indonesia blew. And all of those sulfur dioxide particles and aerosols went into the atmosphere and actually cooled the planet over the next year. And so people have talked about the possibility of using this kind of natural phenomenon to perhaps by injecting these aerosols into the atmosphere to cool the planet. But as we'll talk about later, we'll see that there are some unintended consequences associated with these kinds of what we call geoengineering control measures. We saw that in 2023. I'm sure most of you have seen this in terms of the news media. We had the warmest summer ever that had been recorded since we've been recording temperatures since the 1880s. And we can see how far in July of 2023 we were above the normal. I'm just really blowing records out of the water. And then one last slide just to show you the warming temperatures. Again, looking at this anomaly compared from the long-term baseline at 0 and how much the last few years have been the warmest by far in 2023. Again, this last bar here, we can see how far of an increase we've had since the beginning of the year compared to previous years. Just really unprecedented in terms of the increase. So we know that the Earth's climate is constantly changing. This is one of the naysayers, climate change naysayers say that this could be a natural phenomenon. So the real question becomes how much of this observed warming that we've seen, that we've measured, is due to human activities and how much is it due to this natural variation in the climate? And one way we can take a look at this is we can take these long ice cores. These are ice cores that, are in some places are 100 meters, 500 meters long. And then what we do is using oxygen isotopes and also radio dating, we can figure out how long ago these different laminations are in the ice cores. And then with a fine syringe, we can go in and actually get into air bubbles that are trapped inside the ice core and actually take out the carbon dioxide concentrations that are in the air bubbles and also the oxygen levels. And using oxygen isotopes, we can infer what the temperatures were at that time frame that we had dated from the ice cores. And what we see is that this goes back about 750,000 years. It's about as far back as we can go with any kind of confidence in the data. The Earth has been through 8 of what we call glacial interglacial cycles. When we're during an ice age, from these ice cores, the CO2 concentrations measured in these air bubbles is about 210 parts per million. During the interglacial period, the CO2 had been averaging about 260 to 280 parts per million. And the temperature changes that were inferred between the ice age and the interglacial age was about 8 to 13 degrees Fahrenheit. Now today, in today's atmosphere, we're at about 420 parts per million on a global basis. So we have blown the interglacial CO2 concentrations, again, in unprecedented records. And if the past is prologue, we would expect our temperatures to increase somewhere between 8 to 13 degrees Fahrenheit through this interglacial period. Now, the rise in CO2 has been so dramatic and so fast, whereas these glacial to interglacial periods took thousands of years. We're doing this in 100 years. So we really, really don't have a good feel for what the implications are going to be for this planet because things are changing so fast and in an unprecedented way. Now, having said that, there are a lot of uncertainties associated with climate change, and I want to be transparent about these, and I'm going to talk about 5 of them that we're really facing in terms of understanding what's going on or trying to understand what's going on around the planet. The first is that climate change impacts are not going to be uniform across the planet. The reality is that there are going to be some areas like the Arctic Circle that are warming much faster than others. And as a consequence, and I put this in quotations, there will be winners and losers around the planet. There's going to be hotspots, again, around the poles. We can see during an El Nino year in the Atlantic, particularly in the Pacific Ocean, along the east coasts, east side of the Pacific Ocean or the west side of South America, also in the desert southwest of the US, in northern Africa and parts of Asia as well. We're seeing particular warming areas. Now, the polar vortex that hit us about a decade ago, this is in Chicago on Lakeshore Avenue, and so people would say, oh my God, how can we be having climate warming, having this polar vortex? Well, the reality is during this polar vortex where we had this blob of very cold air coming out of the polar region and settling down across North America, we were having record warm temperatures across northern Asia, up to 10 degrees Fahrenheit warmer than normal during this time period, Celsius during this period. So some really significant warming trends going on while we were cold. So yes, all weather is local and we can feel it here, but when we think about climate, we have to think about it on a global basis. And in fact, on a global basis, we were warming about 0.6 degrees Celsius during this so-called polar vortex that was hanging over us. And in fact, when we look at the US on a statewide basis, since 1970, when we had the first Earth Day, we can see the states that are having the warmest or the fastest growing, this is degrees of Fahrenheit per decade. So up close to 1 degree Fahrenheit per decade. We can see that across the northern Midwest, we're seeing this. The Northeast in particular, and again, the desert Southwest are experiencing the warmest temperature increases. So as I mentioned earlier with Pinatubo, some aerosols will cool the planet. During these volcanic eruptions, there's going to be sulfate put in. This is Pinatubo and the impacts, and you can see how much is going into the atmosphere. And as a consequence, the sun's rays are now being blocked from reaching the Earth's surface, so we're getting this cooling effect. We'll have climate feedbacks as well. And this can either amplify or dampen the climate response to the heating forces that are going on in the planet. And probably one of the most critical feedback loops is what's happening with water vapor. Because the more greenhouse gases we get, we trap more heat in the atmosphere, we warm the temperature, we get more evaporation, and this water vapor goes into the atmosphere. The question is, does it stay as water vapor or does it form clouds? Because if it forms clouds, then we're going to have greater reflection of the sun's rays, and that will result in cooler surface temperatures. So we have this decision point of whether this water vapor forms cloud droplets and cools, or whether it stays as water vapor and it warms. And this is probably one of the biggest uncertainties associated with the general climate models that are out there. As a consequence, these climate models often are uncertain, and so we just don't know what's going to go on. The third major uncertainty deals with ocean circulation. The oceans move around according to what we call a conveyor belt. They're not random in their distributions and circulation. There's actually a fairly well-known circulation pattern. And the ocean, of course, is really important in storing carbon dioxide and heat. In fact, we would expect the temperature to be about twice as warm as it's been if it hadn't been stored in these oceans. And here's the conveyor belt. The red is the warmer saline water that's on the surface of the oceans. The blue is the cooler water. It becomes denser, it sinks, and it moves south. So if we look at our Gulf Stream here, coming off of North America, it crosses the Atlantic and then goes into the northern part. It actually keeps Scandinavia and Northern Europe warmer than it probably should be given its latitude, thanks to the Gulf Stream. But then it starts getting cold and it gets denser and it sinks off of Greenland and then starts its way back down south again towards the South Pole. It splits, some of it goes up into the Indian Ocean. It starts to rise with warmer temperatures and then comes back to the Gulf Stream. The other part of it splits and goes into the Pacific Ocean, again heads north and then rises and then comes back and then forms into the Gulf Stream. The problem is this area right around Greenland and Labrador, because the Greenland ice mass is melting. And as a consequence, fresh water is starting to dump into this area. And it's uncertain if this will change the balance of that circulation. Will it continue to get dense and sink, or will that stop? And if it does stop, this has huge implications for climate on a planetary basis. And we just don't know. Because of this is such a critical area, now there's between Northern Europe, the Europe Horizon forces, and also the NOAA, our National Oceanic and Atmospheric Administration, are putting more and more sensors out into this region of the North Atlantic to get a better handle on whether this conveyor belt is shifting or not. We want to understand it better. A recent study that was done a few years ago showed that the ocean circulation currents between 1990 and 2013 have increased by about 15% per decade. They're thinking that stronger tropical currents could carry more warm water to higher latitudes. But because CO2 is less soluble in this warmer water, that could slow the ocean's uptake of CO2 from the atmosphere. So that's just one of the many implications associated with these changing circulation conveyor belts. As I mentioned earlier, ocean storage is really critical for storing CO2 and temperature. Teleconnections are these connections that are occurring in the atmosphere across the entire planet. This is be like El Nino and La Nina, where the impacts that are, or the effects that are going on in the Pacific Ocean and in the Atlantic Ocean as well, are affecting our climate here on land. So El Nino, the boy, is when we have this warmer Pacific Ocean water heading towards South America. La Nina is when it's cooler water heading towards South America. And this has implications for the climate in the United States. During La Nina, which we had the last couple of years, we get the cooler air coming off of the Pacific Northwest, and we would be wetter and cooler here in the Midwest, whereas El Nino, which we're entering into this year, and it could be a pretty strong one, will result in slightly drier and warmer conditions. Also, in addition to El Nino and La Nina, the North Atlantic also has an oscillation phase, which can affect us as well, where we can have positive and negative phases again around us. And then finally, we take all this information and we generate these general circulation models, or GCMs. There's about 20 of them that are being developed around the planet. They are very computationally intensive. They take a lot of computing power. These are very complicated models. But this ensemble of 20 are usually run together, or some subset are run together, to see whether they have consistent patterns or whether there's inconsistencies that are shown here as part of that. And here's just one example. This is in terms of clouds on the top row and precipitation on the bottom. And you can see precipitation models. These are 4 major models from different parts of the world. They're somewhat corresponding pretty well across the planet, but you can see in terms of clouds, we see dramatically different patterns for these 4 different models. And as I mentioned earlier, that water vapor in the atmosphere really affects whether we get clouds or whether we get staying as water vapor and not forming clouds. And because these models are really uncertain as to what will happen, it's reflected in these outputs, which are not consistent at all. So we're still learning. This makes the prediction about what climate impacts will be very difficult. So that leads us to what might the future hold. And everybody asks, what is your prediction with respect to the impacts of climate? And I usually like to show this cartoon to give you an idea. And I think this is holding pretty true in terms of our understanding. Now, we do have some things that we know pretty well. For example, as I'll show you in this was a study that was done a few years ago where about 20 scientists and experts came together under the auspices of the Environmental Law and Policy Center in Chicago to look at what the impacts would be. And I want to show you the data for precipitation, temperature, and snowfall, so you get an idea of what the best guesses are based on the models that we're talking about. So this is change in temperature. 1986 to 2016 is the observed trend, and then it compares it against 1901 to 1960. And we can see that we have 2 columns here, one for the states bordering the Great Lakes, but let's focus on the far right column, which would include Michigan, the 8 Great Lakes states that we have here in the basin. And we see that over this time period, the temperature has increased about 1.6 degrees Fahrenheit. And then we look at what the climate scenarios are for the future. And we have 2 different scenarios. The lower scenario, which means that we would start addressing climate change and start to decrease it. The higher scenario means business as usual, where we don't do anything at all. And you can see over the next 30 years that if we even starting to make changes in climate and reducing the CO2, we're still going to get a 3-degree Fahrenheit increase by the mid-21st century. If we're looking at the highest scenario, it goes to 3.3 degrees. Now we go out another 30 years, and we can see that we expect the temperature under the low emission scenario to be about 4.5 degrees Fahrenheit increase, and under the high emission scenario, about 5.5 degrees Fahrenheit. And then we go out another 30 years to the end of this century, and we can see it's about 6 degrees Fahrenheit versus 10 degrees Fahrenheit by 2100 if we continue business as usual. What about precipitation? Precipitation is a little less certain than temperature. What we've seen is about a 10% increase in precipitation over the last 30 years for the Great Lakes states. What the prediction is that there will be a decrease over that time period to about a 4% increase compared to previous times, but that would be less than what we've experienced the last 20 years. And then if we go out to the mid part of this 21st century, we've got a 6% increase and a 7% increase. And then finally, way out to the end of the century, we have a 7% increase compared to the early part of the 20th century, and an 11% increase. What does that mean in terms of snowfall? Well, my recommendation is to disinvest from ski resorts and invest in water parks, because our snowfall is going to go down dramatically, about 30% under the low carbon emission scenario, and up to 50% in the high carbon emission scenario. So this is really significantly impacting our winter sports, and also things like ice fishing, because the temperatures will be warming as well. So some serious, significant recreational implications. What about the impacts to aquatic ecosystems? And I'll particularly focus on, again, water temperature and precipitation. We expect lake water temperatures to increase. We've already seen that. This was a study done about 7-8 years ago. If the lake, these are all lake sites, if they're in red, it means that they've been increasing over time. And if they're in blue, and there are a few of them, they've been decreasing over time. But overall, you see a significant increase in temperature over time in these lakes. And what we see is that the lakes are actually warming slightly faster than the atmosphere or the ocean at about 1/3 of a degree Celsius per decade. And this has implications as well, as I'll talk about. In fact, back in July of 2020, 3 summers ago, we saw that in terms of degrees Celsius, up to 4 degrees Celsius, Lake Michigan was about 10 degrees Fahrenheit warmer than normal in July back in 2020. And this was occurring through most of the Great Lakes other than the eastern central basin of Lake Superior. Everything was warming, particularly along the lake shores. So unusually warm temperatures, unprecedented temperatures for the Great Lakes. And of course, most fish, if they want to stay in the nearshore area, are going to be really impacted by this. If they have the ability to survive in the deeper waters or in the open water, they're going to move to areas where it's cooler. So for precipitation, most of the models suggest, and this is again with a lot of uncertainty, that the annual average precipitation will increase slightly in our region. But what will change with a bit of stronger prediction, more confident prediction, I should say, is that the frequency of extreme events will increase. And by extreme events, we're talking about heavy precipitation, heavy snowfall when it's cold enough to snow. And the reason for this is simple physics. For every degree Fahrenheit that the atmosphere warms, it holds about 7% more moisture. And so the atmosphere is holding more moisture, and then when it does release that moisture, whether it's rain or snow, it's going to release more of it. So we're going to get more of this dumping. And this has implications for our infrastructure and for our society, because the way that our wastewater treatment facilities were built and our stormwater facilities were built to handle that kind of runoff, they really weren't made to handle these kinds of 100-year events that are now occurring every 10 years. So when we get a massive event that more than 2 to 2.5 inches of stormwater, it's containing all these contaminants that are running off. They're running off our farm fields. They're running off of our driveways that might have pollutants on it. It's running off of our rooftops, and it's got contaminants in it. And because these wastewater treatment facilities can't handle this much precipitation, what they do is what the EPA euphemistically calls blending. They actually will blend, they'll dump this raw sewage that they simply can't treat. They don't have the capacity to treat it into the waterways, and it's blended with the presumably uncontaminated water in our system, because they just don't have the capacity to deal with it, because now we're getting more of these rain events that they simply were not built to handle. And it's anticipated that the frequency of these events exceeding this 2.5 inch threshold are going to increase somewhere between 50 and 120% by the end of the 21st century. In fact, if you look, this is between 1958 and 2012. So this is the most recent data, 10 years ago. We can see how often this heavy precipitation is occurring in that time frame for the later part of the 20th century. Up to 70% more often that we're getting these heavy precipitation events in the Northeast, and almost 40% in our region. So we're already experiencing this impact, and we're seeing this. We're seeing more contamination. We're seeing more beach closing. Of course, we're getting better at testing for these pathogens, but nonetheless, we're seeing more pathogens on our beaches. And then if we look over the continental US, this is the trend in these one-day 100-year rainfall exceedances. Oops, sorry. And we've gone from about 6 up to about 10 or 11. Obviously there's a lot of variance around here, but the trend is increasing, clearly increasing over time, where we're getting more of these kinds of large storm events that are carrying more pathogens. And again, looking at heavy rain events, we can see the deeper the blue, the greater the probability that we're going to get heavier rain events. And again, this goes to the point I made earlier that there's going to be winners and losers around the planet. I mean, of course, if you're going into no rain at all and drought, you're creating a whole new problem. But if you have too much rain, then you have this problem of too much runoff containing nutrients as well as pathogens. And this occurs on a localized basis. This is a storm drain going into Mona Lake here over on the lakeshore in West Michigan. And you can see that there's a storm drain here that's draining. It probably shouldn't be draining any water because the conditions are dry. So there might be some illicit connections. But then we get this massive storm event. And what happens is all of the garbage that's being taken off the roads and going into our storm drains, because they go directly into our waterways, are being trapped behind this grate that you can see here. And the force is so large that it actually causes the pipe to break with the pressures behind all this litter behind the grate. And in fact, the pressure was so large that the entire pipe was disengaged from the embankment, the bridge abutment from the system. And of course, that's something that's probably not in the Norton Shores budget to deal with. And this is a function of getting these massive rain events that we simply the infrastructure was not built to handle. It also can cause these culverts to give way and the roadway then to disengage. This is up in Manistee County, again, from a big rain event. And these kinds of events are happening more frequently. In terms of our waterways, our natural waterways and lakes, the implication of having these warmer temperatures means that the lakes that stratify, and most of our lakes around here do stratify, you have that upper warm layer in the summer and then the colder bottom layer. And that's separated by what we call a thermocline. This thermocline and stratification will occur earlier in the year because the temperatures are warming faster, and it will last longer into the season. So if we see this diagrammatically, we see in the spring when the temperatures are what we call isothermal, or the same from top to bottom, any kind of wind event will turn over the lake and it will completely mix. And this is healthy for the lake. You're restoring the oxygen down to the bottom. The nutrients that are accumulated in the bottom will then be taken to the top and taken up. And so the lake becomes healthier. In the summer months, the lakes will stratify. And as I'm saying earlier, now that stratification will occur into the early to mid-spring and it'll last into the fall. And what will happen down at the bottom layer, where you're no longer getting oxygen down to it because of this thermocline, this temperature gradient, there's still respiration going on here by fish, by bacteria, by other kinds of heterotrophs, and they can actually deplete the dissolved oxygen concentration. And the longer the stratification goes, the greater the opportunity for this hypoxia or anoxia to form in this system, which can cause fish kills and change the phosphorus biogeochemistry in the lake. And then in the fall, when the top layer starts to cool again and the temperatures become isothermal again, then the lake will mix again, but that's going to occur later in the year. So there's certainly some very significant implications from warming lake temperatures with respect to stratification. And we've seen this in Muskegon Lake. We have a buoy out in the lake, and it's been monitoring. It's about 40 feet of water, and we have sensors about every 5 to 10 feet down. And we can measure both water column temperature and dissolved oxygen. I want to point you to the bottom panel here. And you can see we have DO sensors at about 6 feet, 15 feet, 25 feet, and down near the bottom at 35 feet, 36 feet. That's the black. And you can see in the summer months from July through September, in this case, the data are 2011 and 2012, but it happens every year. Basically, there's no dissolved oxygen at the bottom of Muskegon Lake, which is something that we did not anticipate. The hydraulic residence time, or the amount of time a water molecule stays in the lake, is about 22 to 25 days. And we didn't think there'd be enough time for basically dissolved oxygen to be depleted, but we were wrong. The middle of the lake does go hypoxic. And we're seeing glacial lake changes as well. That's occurring during glaciers. As the glaciers are melting, more lakes are forming. We've seen that the number of these glacial lakes have increased about 50% on a planetary basis. In area, again, it's increased about 50%, and in volume, about 50%. And this has significant implications because these glacier lakes that are formed as these glaciers melt don't have any permanent dams behind them. So eventually that force of the water is going to cause these, the earthen dam that's holding the water back is going to burst, and it can cause death and destruction. So we're seeing this in the anywhere, particularly in the Himalayas, but anywhere where there's glacial lakes. And then, of course, we have harmful algal blooms. For the cyanobacteria or blue-green algae that form these blooms, they need a couple of conditions to really become problematic. One is they need nutrients, and they certainly have enough of that in our lakes around here. And then also they need warm temperatures. A lot of these blue-green algae will form overwintering spores, or the technical term are aconites, and they sit in the sediment. And when the sediment becomes warm enough, they will germinate and they will form the inoculum for new blooms. And we can see that the amount of algal blooms around the nation continue to increase in number. It's not a phenomenon that is unique to Michigan. We see this problem all over, and the blooms are normally based on how much chlorophyll A is in the lake. And there's different thresholds or standards. Some agencies say 20 parts per billion or micrograms per liter of chlorophyll is enough to categorize as a bloom. Some use 40 micrograms per liter. We get these blooms in Muskegon Lake. We had one in October, and we're seeing these blooms last longer into the season. In the past, the temperatures would cool by September, and we'd be done with these blooms. Now we're seeing them in October. This was a couple of weeks ago, and even into November. And a close-up of the bloom that we had back in about a couple of weeks ago in Muskegon Lake. Now, the most common genus that forms these blooms is Microcystis, and they form a toxin called microcystin. Don't blame me, I didn't come up with these terms. It does get confusing, but microcystin is the most common toxin produced by the blue-green algae and the harmful algal blooms. It's a hepatotoxin, will affect the liver and also promote tumors. There are different standards. The World Health Organization, or WHO, has standards of drinking water of 1 part per billion and recreational standards of 20. The US EPA recent standards that have just been promulgated for drinking water, they're down to 0.3 parts per billion or micrograms per liter for infants. And then from 6 years and up, it's up to 1.6 parts per billion if it's drinking water, 8 parts per billion if it's for recreational use. So we do measure the microcystin concentrations in our blooms. And if we look at some of the lakes in our region, we can see in Mona Lake, a massive bloom back in 2007. Now, that's not a drinking water source, but for recreation, remember the threshold for EPA is 8, and we're way above that at 350. Lake Erie, the bloom in 2011, that was not the bloom that caused Toledo to stop its drinking water, but it was actually a very, very toxic bloom with concentrations up to 4,200. 2014 was the bloom that closed down the drinking water for Toledo. And the concentration was actually much lower, but the bloom formed right by the water intakes, whereas the 2011 bloom was out in the middle of the lake, not near the intakes. Muskegon Lake, back 2 years ago, we had concentrations of about 1,000 micrograms per liter of microcystin. And then the bloom I just showed you a couple of weeks ago was about 8. So again, that's at our recreational standard, which is Muskegon Lake, again, is not a drinking water lake. So we're right at that EPA threshold. The Toledo crisis, as I mentioned, the microcystin concentration wasn't that high, but it was right at the water intake. And of course, it did exceed the 1.6 or 0.3 standards for drinking water, depending on whether you're an infant or not. And it impacted mostly the poorer communities. There's a real environmental injustice component to these kinds of issues, and it had significant economic impacts as well. Where in Toledo area alone, it was estimated to have a economic loss of about $65 million just over those 3 days. And then when we look at the effect of cyanoHABs in Western Lake Erie on a yearly basis, it's about $71 million. And these blooms should not, they're not a surprise to us. We expect them. We have plenty of nutrients, warmer temperatures, and we can predict with pretty good accuracy what the extent of the blooms are going to be based on when the agricultural fertilizer has been applied to the field and if it rained immediately thereafter. And all those nutrients get into the waterways and eventually work their way down to Lake Erie. And it's no different from Lake Erie than Lake Makatawa or any of these other drowned river mouth lakes that have an agricultural land use. And even an urban land use also can contribute nutrients. And these blooms are variable. This is looking at years from 2002 through 2017 in the western basin of Lake Erie and the central basin. And you can see that, some years the blooms are incredibly significant and some blooms are not very significant at all, again, depending upon whether there was rainfall after the agricultural fertilizers have been applied. And so blooms are spatially variable throughout the entire Great Lakes. This is phosphorus concentrations, which of course help stimulate the blooms back in the springs of either 2013 or 2014, depending upon what lakes you're at. And you can see that in the embayments, the western basin of Lake Erie, Saginaw Bay, Duluth Harbor, we tend to get the highest concentrations of phosphorus from runoff, and that's where the blooms tend to form. So what can we do as a society? And when we talk about actions, they're usually broken down into two categories. One is mitigation and one is adaptation. I apologize for that typo. I really need to fix that for adaptation. So with mitigation, which refers to the fact that we are going to try and stop the climate change. We're going to do something. We're going to take an engineering approach. We can either accelerate decarbonization, which means that we're going to put more renewables out there and move away from burning fossil fuels, and then reduce the industrial and agricultural carbon emissions. The problem is that we're currently deploying the renewable energy at a woefully short pace, nowhere near where the Paris Agreement was to hold Earth's temperatures no more than 2 degrees Celsius above pre-industrial levels. There isn't enough of this sense of urgency around us for whatever reason. And then the idea of removing CO2 from the atmosphere, the carbon dioxide removal, or CDR. There are 3 main approaches that are being suggested around this. Each of them have their own implications. There's blue and green carbon, which is reforestation around the planet, plant trees, and then coastal restoration, plant seagrasses, emergent vegetation. Again, try and stabilize the sediment and have these plants suck up CO2 as part of photosynthesis. BECCS is bioenergy with carbon capture and storage. In other words, we're growing trees. We're then burning the trees to generate energy, but the CO2 that's being emitted as part of the burning process is captured and stored deep in our geology. And then finally, geoengineering, where we're talking about manipulating our planet in order to deal with the carbon problems. And I'll talk about these a couple of the geoengineering suggestions. I've already mentioned the idea of pumping aerosols into the atmosphere to deflect or reflect the sun's rays. Let's talk about BECCS, the bioenergy. As you can see, we're growing trees. We then harvest the trees. We burn them in order to generate energy. And then that CO2 that's being emitted is then captured and buried deep down in our geology. And when we look at these 3 different carbon dioxide capture methodologies, the first, we talked about blue and green kind of carbon storage, and we look at the 5 different categories that are associated with that. As low engineering complexity, we basically plant the trees. There's high co-benefits in the fact that we're creating habitat in the process. You need a lot of land to make this scalable. There is a risk of CO2 release, a high risk, and the energy status overall is neutral. If we now go to BECCS, there's a medium level of complexity, engineering complexity. There's low environmental co-benefits because the habitat you're creating, you're cutting down. Again, you need a lot of land to make this scalable, to create enough bioenergy. There's a low risk of CO2 release because now you're capturing it. and there's a net energy production as a function of the energy being produced from the burning of the biomass. And then finally, direct air capture, that's highly complex. Again, low environmental co-benefits. There's a low amount of land area needed because you're now sucking it out of the atmosphere. Low risk of CO2 release, but you're actually taking more energy to capture it than you're using more energy to capture it than you actually produce. So what about geoengineering? We mentioned earlier this idea of reducing the incoming solar radiation. Some ideas are, basically pumping these reflecting particles into the atmosphere, or maybe putting shields out into the troposphere, which will lead to decreased temperatures, but may lead to these unanticipated consequences. If we look at what happened after Pinatubo, you can see these aerosols in the atmosphere. But if we look at basically the blue is discharge of water and the yellow is precipitation, we can see during the Pinatubo period, we had droughts on a planetary basis. We had less runoff, we had less rain because obviously we had less evaporation because there was less heat in the atmosphere. And so if you're willing to cool the temperature at the risk of drought, is that a worthwhile trade-off? Then you've got a solution. But I would suspect that if you're in a drought area, this is not going to be the solution that you want. So we have to really understand the implications associated with these geoengineering solutions. Another one that's been suggested is iron fertilization. There are huge swaths of the ocean, particularly in the North Pacific, where there's plenty of nutrients for algae to grow, but they're not growing. So the question is, why do you have these high nutrients but low chlorophyll? And due to studies that were done in benchtops, they found that these areas of massive areas of the ocean are actually iron deficient, that these algae needed the iron to grow. And when you fertilize the oceans with iron, which was done back in the late 90s, in fact, you got this big phytoplankton bloom. The phytoplankton would obviously photosynthesize, take the CO2 out of the atmosphere, eventually die. And as they sink, the carbon that's trapped in those particles sink down to the bottom of the ocean and trap it there. The problem is that the algae that grew in the oceans were the kind of algal cells that the zooplankton don't feed on. And the zooplankton are the food source for the fish. So if you want to have a fish community in the oceans that are harvestable to eat, you need the desirable type of algae. And that's not what was growing as a function of this iron fertilization. So again, another unintended consequence from this, what otherwise would be considered a very good idea. So, and in fact, the interesting thing is back in the late 90s, when they saw that this was working, there was a lot of monetization around these ocean vessels to do fertilization by iron, particularly in the Vancouver area in British Columbia. And then when the oceanographers saw the implications, the very negative ecological implications from iron fertilization, the Canadian government put a moratorium on doing any kind of iron fertilization, and that moratorium is still in effect while studies have continued to go on for the last 20 years. There's a lot of mitigation activities going on around the United States, both at the state level and at the local level. As you might anticipate, California, Oregon, and Washington and Colorado are probably the most progressive in terms of these kinds of activities. As you can see, the activities can be basically doing carbon capping and pricing, going to renewables is the blue, putting in more mass transportation is the purple, being more energy efficient in the yellow, having non-CO2 greenhouse gases emitted, and then forestry and land use, basically planting trees in green. So lots of activities going on, but still the planet continues to warm. I'm going to blow through this because this is way too complicated. My apologies. So what can we do at a societal level? On the adaptation side. So we talked about mitigation. Now let's move to adaptation, where we accept the fact that the climate is warming. And so we need to adapt to that. And that's not to say that we give up on mitigation, but we also try and be more realistic about what's going on. Basically, we may have to change the crops that we grow in our region to reflect different grow zones with warming temperatures. Change our zoning and building codes so that we become more energy efficient, perhaps put in renewables, capture our stormwater runoff, all sorts of different ordinances that can be done. Change human behavior, that's usually the most difficult thing to do. We are very resistant to doing that, but all sorts of behavioral changes we can do, and I'll talk about those at an individual level. And then nature-based solutions, where instead of using what we call gray infrastructure, we go to green infrastructure. Let's not have all these built solutions, whether it's seawalls to protect our shoreline. Let's have a natural shoreline where we have vegetation there, which is going to stabilize the shoreline. It's going to create habitat. It's going to take up carbon dioxide. Runoff, instead of having impervious surfaces, hardened surfaces, let's do porous surfaces, or let's put in more wetlands in order to capture the water on site instead of it going through our storm drains. All sorts of those kinds of activities. Here's an island in Alaska, which is due to sea level rise, was being threatened. So they decided that they were going to basically raise the island and put riprap around it in order to protect them. If we have stormwater retention, we may not have these kinds of flooding events. Now, some flooding events, if they're really significant, 8 inches in an hour, no amount of green space or retention devices are going to hold it back. They're going to have these flooding events. But for these, mini events, these 1 to 2 to 3 inches, having rain gardens, stormwater detention areas, wetlands can help mitigate these kinds of problems. Here's another example where, and this is in Philadelphia, outside the Philadelphia area, where the runoff from the road is now going through this barrier area and then goes into a little green space, which is aesthetically very pleasing, but also serving as a stormwater detention device. So as an individual, these are things we can do. They do make a difference collectively, but people don't feel like, it's that significant. So perhaps there's a resistance to doing it. I would still implore all of us to be more cognizant of the electricity and power that we're using. So when you don't have when you're not watching TV, turn it off. Same with the lights, same with the computers. If possible, use mass transportation or a bicycle or walk instead of using an automobile. If you are a meat eater, as I mentioned earlier, not only do you have methane coming out of these cows that are being grown, but in addition, it takes an enormous amount of water, about 200 liters of water to produce 1 pound of beef. And that's because you're using all that water and fertilizer to grow the grain to feed the beef. And so you have to think about the upstream consequences of meat consumption. Plant trees, they absorb carbon dioxide and they tend to last a while. Recycle, that's really critical. It helps save our natural resources. If possible, buy low energy appliances that have Energy Star rankings. If you can, go to renewable power for your home. Also, try and be more buy gas efficient automobiles, hybrids, or go to electric vehicles. These are not panaceas, but they can make a difference. There's a lot of movement about studying and discussing this issue with others to, educate people, have discussion groups about these kinds of climate issues. They are impacting not just our current generation, but certainly future generations. So it behooves us to make sure that we leave this planet in a better condition for our children and grandchildren. You can have playing cards now that talk about the climate. And so you can use this as a game and learn in the process. And then finally, the most important thing, in my opinion, is to vote wisely. You want our elected officials, whether this is at the local, state, or federal level, to be informed about these kinds of issues and to be voting in a way that is consistent with your own value system. Again, this just gives you some examples of things that you can do on a household or individual level. And they're broken into 4 categories around food, energy, travel, and waste. But just looking at the top 5, reduce food waste, because that goes to our, unless you're composting, it's going to be going to our landfills where it will start to decompose and form methane, which, as we know now, contributes significantly to warming of our atmosphere. Go away from meat towards plant-rich diets. If possible, be using photovoltaics, insulate your home, go to LED lighting as opposed to incandescent lighting. The good news is, I don't want to be a prophet of doom here, is that what we're seeing is that there is an increase in the use of clean energy, and the price of clean energy is going down. So the trend is in the right direction. And what are the consequences if we don't do anything, if we don't mitigate or adapt? Well, here you can see that the anticipated temperature changes. This is in Fahrenheit. The warmer the colors down in the legend on the bottom, the warmer the colors, the more temperature increase. Again, we have our low scenario, low emission scenario, and our high emission scenario on the right, low emission on the left. And you can see by late 21st century, if we really don't do much in this area, we're going to see temperatures in Michigan that are increasing about 8 degrees Fahrenheit. That basically puts us in the summer months somewhere around Arkansas, and in the winter months around southern Ohio. The Intergovernmental Panel Climate Change Report found 6 major findings with respect to water. This is from a year ago. One, that these climate impacts are accelerating, that humans are responsible in large part for making them worse. As a consequence, our food and water security are in jeopardy. Also, human health is at risk, particularly due to heat waves. And the older generation that don't tolerate it or don't have air conditioning are at risk, again, an example of environmental injustice. The reality is that the older generations are more vulnerable than others, and that according to the IPCC, there's still time to act, but that window is narrowing. And then finally, I'd like to end with this quote that humans cannot at their pleasure command the rain and the sunshine, the wind and the frost and the snow. Yet it is certain that climate itself has, in many instances, been gradually changed and ameliorated or deteriorated by the human action. And the reality is that this quote comes to us from the 1850s, or 1847, by the Vermont Senator George Perkins Marsh. And so we've known about this for almost 2 centuries, and we have still to do much about it. That one's already done, so I'll leave you on this final thought. This is how climate change scientists drown their sorrows. So I want to thank you for listening, and if there's any questions that people may have about this, then by all means, they can contact me or go to Tanya, and she can be in reach with me as well. Thank you very much.